In this video, we will go over how to solve the heat equation, this partial differential equation, using Crank-Nicholson, which is an implicit method. Okay. Again, I won't go over the details of the derivation, but using finite difference formulas, you can derive this particular equation. This particular equation is formed by using these 4 points. These 4 points. 1, 2, 3, and 4, and you can see up here this is t in position x and the previous time t minus k, which is this blue point over here, and then on the left hand side we have t of x and t, which is this point here that we are interested in, and the one on the left and the right are x minus h and x plus h at that time scale. Okay, so this gives us one equation but two unknowns, because you have these two green dots that you need to solve for. Okay, so what we do is we go to the next, so this forms the first equation, so we'll go for the next 4 points like this, and this will give us two equations, but we now added another unknown over here, which is this point here, so we have 3 unknowns. So this still doesn't help us. Okay, so we have to keep going all the way till the end. Over here we'll use the next 4 points, so now we have 3 equations and we still have 3 unknowns. Okay, so you can then use any kind of linear algebraic methods to solve for these 3 equations, to use these 3 equations to solve for the 3 unknowns. When you put this 3 equations in matrix form, you will end up with an equation that looks like this. So these are the green points, okay. The 2 red points that you see here, the boundary conditions here and here, will show up over here as U01 and U41 here. Okay, and these are the initial conditions, U10, U20, and U30. Okay, these are time 0. These are the initial conditions. Okay, so all this right hand side is known. So and you have lambda as well. Lambda we already know is lambda is k over h squared. So everything is known. The only unknown is this vector of u, which are the green dots, and you can solve for them using one of the linear algebraic methods. Okay, so let's see how to encode this. Now, one thing I want you to note is this is called a sparse diagonal matrix. So you have elements only on the diagonals, and we'll see how to create this in NumPy. Okay, once you know how to create this in NumPy, the rest is easy. This, by the way, is the solution only for this particular line over here. Then you have to use a for loop to solve this again and again repeatedly as you go up in time. Okay, so let's look at this. So just like last time, let's try to solve this problem here. So first we define our x vector, np dot a range from 0 to 1 with a step size of, let's stay consistent, so the step size in the x direction will be h. So let's say h, and we'll define h as 0.25, and this will give us our x. So we have to first import NumPy as, okay. So just like last time, this doesn't go all the way to 1. To fix this, just make sure you add a step size to the last value. Okay, so this works. Now our t vector is np dot a range 0 to 1 plus k. We'll use k as the step size for the time direction, 25, and just confirm it's the same, 0 to 1. Yep. All right. Now we have both these vectors. We would like to define the boundary conditions. And on the left boundary we have values of 0, and the right boundary we have values of 1. And then initial conditions equal to this line is the initial condition, and we can see it's sine of pi x. Okay, so np dot sine of np dot pi times x. So we define all these. Now we have to create an empty temperature vector called t, which holds all these values inside it. So we say t equal to np dot zeros, and you give it the tuple size n comma m. and n comma m is found from the length of x, and m is the length of the time vector t. Okay, so the first input or the first row numbers is based on the length of x, and the column numbers is based on the length of the time vector. Okay, to set the boundary conditions, you have to choose where x is 0, so the first position value, and all time values, so first row and all columns. So first row, which is 0, and all columns equal to boundary conditions, the first boundary condition. Okay, and for the last column, the last row is going to be -1 comma all equal to boundary of 1. Okay, just like in the last video, we mentioned that we are using the first index to represent position to be consistent with this formula. The way it's visually represented here will be like a transform version of it. Okay, when I say row, this is not a row, this is the row. Okay, so let's have a look at, now let's also include the initial condition. So the initial condition is this part here. So all position values and the first time value. So all position value is all, and the first time value is 0, equal to initial conditions. Let's have a look at the temperature vector t, temperature matrix t, and you can see it's in scientific notation. So let's just round it up to see it properly. So this looks, oh, the boundary condition here was not 1, it's 0. So both boundary conditions are 0. So you can see I made a mistake over here. So let's run this again, and yeah, so these are all zeros, and you can see these are the initial conditions: 0, 0.7, 1, and 1, and 0.7 again. Okay, and you can see sine 0.25 pi is pi over 4, which is 0.7. So this seems to be correctly defined. Now the next part is to write your the equations for the explicit method. Okay, so for this we first need to find the factor lambda. So like we said in the previous video, lambda is a keyword for Python, so don't use it. We can use something like factor, and the factor is calculated as k over h squared. Okay, so that's our factor. Now we need to create this matrix and this vector over here. So this matrix is easy. Let me add another cell over here to show you how to create a diagonal matrix in Python. So you can create a diagonal matrix using the diag function, and you can write in the numbers that are supposed to appear on your diagonal, and it will show up like this. Now there is a second argument you can add here which tells Python on which diagonal it should fall. So by default it will fall on the main diagonal, but if you have an offset diagonal, you can do that as well. So for example, if I say 1, the numbers will now show up on the diagonal on the right of the main diagonal. Okay, if I say -1, it will show up on the left side of the main diagonal. Okay, so this is one way in which you could form this matrix. So yeah, so in our case, if you wanted to form this, we would have 1 plus 2 lambda here. So let me just, for the sake of argument, I'll just put a number here, factor equal to 10. Okay, and then the first element is going to be 1 plus 2 times factor. Okay, and instead of copy pasting this however many times you have it here, if you have seen Python, when you create a list, you can multiply a list with a number, and that number is then copied however many times you multiplied it with. Okay, so we'll use this feature over here. You can multiply it with, let's say 3 in our case, because we need 1, 2, 3 over here. Oh, this has to be 0 by default. Okay, so this adds this diagonal elements. Now for the off diagonal element, the factor is going to be negative. So np dot, so we'll add that matrix into this one. So np dot diag, and it's going to be negative factor. Okay, and you have to be careful of the numbers. If you multiply it with 3 and then set it to a -1, you have the sizes mismatch. This one is going to be a 3 by 3 matrix, and this one is going to be a 4 by 4 matrix. So you shouldn't be multiplying with 3, you should be multiplying with 2. There's only 2 values over here. Okay, so this should have been 2. Okay, so let's do that over here. It should be 2. And let's have a look at A. So this took care of the bottom part, and for the top part you just have to implement the same thing in p.diag minus factor multiplied by 2, but this time instead of -1 you push it to the other side by using 1. Okay, and we have everything in order. Okay, so and one thing you should notice is that this left hand side matrix over here, it is not affected by which row you are on. Okay, it's just a couple of constants, which is a function of lambda. Okay, so you just need to define this once, and then we can move on to the rest of the problem. For the rest of the problem, we have to write a for loop to change the right hand side of this equation. Okay, so if this is u1 comma 0 for the first run, it's going to turn into u1 comma 1 for the next run. Okay, so this has to be recalculated inside a for loop. So what exactly are the right hand side points? Okay, this is these 3 points are the blue points over here. Okay, so it's the previous level except the boundary values. Okay, and then for the topmost value you add lambda times one of the boundary condition, which is on this side, and the other one is plus lambda times the other boundary condition, this one here. So we have 1, 2, 3, 4, 5. These 5 values are what forms this particular matrix, particular vector. Okay, so the first thing you can do is you should create this vector over here, and then just add this value to the first index 0, and then you add this value to the last index, which is index 2 in this case. Okay, so let's see how to do that in Python. So in this particular case, we have to extract it from here. So it's going to be the 0.7, 1, and 0.7. That's the first part. So we will have t equal to, or we'll define that as b equal to t, and we want these values, this one, and this one. If you just say b equal to this, you'll get the following. Oh, comma, we only need the first row, right? T of 0. Yeah. Okay, again b dot round to see it properly. So we get 0, 0.7, 1.7, and 0. So we don't want this, and we don't want this, right? We only want the middle 3. So it shouldn't start at 0, it should start at 1, and it shouldn't go all the way till the end. It has to go till -1. Okay, and now we get this small portion, 0.7, 1, and 0.7. Okay, the next step is we need to add this 0 to this 0.7 over here. In this current condition, this is 0, but let's change it for the sake of argument. So I'm going to set this to 10 and this to 10. T dot round. Okay, so we would like to add this 10, the value 10 over here into this one. Okay, so how would you do that? You just say b of 0, okay, equal to b of 0 plus factor times t of what? Okay, this is the next time vector, so we know that there is some row information, comma time is the next one, so it's not 0, it's 1 over here. Position wise, it's in the 0th position. Okay, so we are in the 0th position. It's a boundary condition, but it's in the next time. Okay, and the same thing can be said for the other one, b minus 1, which is the last value in b, this one. Okay, we need to add 10 to that, so b of -1 is b of -1 plus factor multiplied by t. Okay, again, how do you refer to this particular point here? This is gonna be, position wise, is the last one, so it's -1. Okay, and time wise, it's in the next vector here, which is 1. Okay, Now this is not static. You have to keep doing this as you compute the higher up values. So for example, if you would like to find values in this level, which is u12, u22, u33, you have to now form the b vector using these 5 numbers. Okay, you already found these in one iteration. For the next iteration, you'll use them to compute the next set. Okay, and then the same thing happens again. So this calculation has to be done inside a for loop. So these two commands should go inside a for loop, actually starting from here. Let's first confirm that our b is giving us what we need. Yes, so factor was 10 in this particular case, so 10 times 10 is 100, so it's being added properly over here. Now there is one slight issue with this. I'll show you what happens to your t vector. T dot round 3. You can see the t value also has been updated. Okay, this is a slight issue in how Python manages its memory. So when you say b equal to a part of t, the Python doesn't actually create a new variable called b. It actually just assigns the same location in memory. It just assigns it a new name called b. So whenever you make any changes to b, it also changes the original one. Now we don't want this to happen, as this will mess up our algorithm. So in order to avoid this, you can force Python to actually make a copy of this data by just adding this command at the end, copy. Okay, if you do this, it will prevent the updation of t when you modify b. Okay, yeah, you have to reinitialize t first. Yeah, so now t is unaffected and you can change b. Now we would like to put this stuff inside a for loop. So let's do a for loop for the time vector. So for j in range of m, and this b, the index inside b is the same, but the index inside t has to change now. Okay, so it's based on the time. So let's go back and check. In this particular case, we are solving for this one first, in which case j equal to 1. So we're starting at 1 and we go all the way till the end. Okay, so we'll write a for loop that goes from 1 till m. Okay, and the first time we have to use this vector u, which starts at 0. So this has to be 0. So it has to be j minus 1. Okay, and the values on the left boundary condition and the right boundary condition is going to be 0 and minus 1. That's correct, but it's from the next time step. Yeah, so these are in the same time step as 1. Okay, so this has to be j and this has to also be j. Okay, to solve for your temperature values, we will just say t, or solution, equal to, you can just do a dot product between the inverse of a. You can just use the solve function, solve given a and b. Okay, and then print solution. Now this has to be inside the for loop. Like I said, it's printing the solution np.linearalgebra.solve, and these are the solutions that's coming out of your temperature vector. But remember that these solutions have to be plugged back into your temperature vector. Okay, so we have to change this 3 zeros into the first value. Okay, so how do we do that? How do we refer to these 3 positions? In it here, t of, these are the 3 rows here. Okay, so it's the same index as this one. Okay, because we know how to extract this one, right? It's the same index over here, so we can copy paste this index over here, except that it's not j minus 1, it's j. It's on this time position, right? So it's not j minus 1, it's j, equal to solution. Okay, and that's it. So now if you print your solution, and you can print your t vector here, t dot round, and you see your solution show up over here. Let's use the code from the last lab to to plot this and just see how it looks like. So we first have to import the matplotlib.pyplot as plt, and then I just copy pasted the same code from last time, and you will definitely see something weird going on. This has to probably do with the boundary condition set to 10, so let's change it to zeros. 0, run this code, run this code. Yeah, so this looks kind of reasonable, but again, the resolution is quite bad because of the step sizes that we chose. So let's try to go for a smaller step sizes. So I'll change this to 0.025 and 0.1, for example. Okay, so that didn't help. We probably need more discretization in the distance direction, x direction as well. Oh, the factor here, let's remove this because we're calculating the factor here. Let's join all this code together. I'm going to put it here. Yeah, so this is the actual factor value, and let's try to implement it and try to plot it. Yep, so this looks kind of good. Again, resolution could be better over here. We could improve it. Let's change h to maybe 0.1, for example. Now this will increase the size for t, and we have an error here that says there's a size mismatch. Okay, so let's look at A and size of A and size of B before it complains. So it's complaining in line 22. So let's just see the size of A, or let's print A just to see what's inside A. Okay, so this is the mistake here. So you can see A is still 3 by 3, although we have changed both the step sizes. If you look at x, print x is probably much larger now, and even t is also large. Okay, so since x is large, that means you have more green points here. If x is large, you have more green points here to solve. So you have the number of unknowns have gone up, which means your matrix, so this is more, which means your matrix over here has to be bigger. Okay, the size of the matrix is related to the number of unknowns you're solving for. Okay, so this is not reflected here. The reason for that is we chose numbers over here, 3, 2, and 2. Okay, this has to do with the length of x. This is n. Okay, so in this particular case, length of x is 5, 0, 1, 2, 3, 4. So we have 5 elements. So n is going to be 5, but we only need 3 of them, right? So it's going to be 5 minus 2. So this is going to be n minus 2. Put this in brackets. And this factor is going to be n minus 3. Oh, okay, and this also is going to be n minus 3. Okay, now your code should automatically update regardless the size of your x vector or the time vector. Okay, so let's try it now, and hopefully, yes, so now we have a larger diagonal matrix over here, you can see, and it's also providing the full solution here. And if you try to plot this, you'll get a much cleaner plot. Okay, one other issue here is we have some round off error. So in order to avoid this from happening, you can round down t. You can go all the way up in the code over here. Maybe just add a round function over here to like 3 decimals. I think 3 decimals should be fine. 0.075, yeah, so this should be fine. Run this again and run this. Yep, okay.